Sorry to land doing it myself. Okay, so today we're essentially following on from chapter 2, which we started last week, and we continued the work in the tutorials. So last week, essentially, what we looked at is the idea that PDEs, or most of them, cannot be solved analytically. Okay, we've got no choice. We have to use a computational or numerical approach. And the simplest numerical approach is the finite difference method. And what this does is it approximates partial derivatives using finite differences. So the work which you've been doing in the labs is all about trying to derive those approximations. And what we do is we replace the partial derivatives in a PDE with the finite differences, and this produces an algebraic system. Now, algebraic systems are easy to solve. We can do that, and hence we have an approximation of the solution. Now, with numerical methods, and this is any numerical method, we only ever approximate the solutions. We're never getting it exact. So the key sort of point is how do we ensure that our approximated solution is as close to the exact solution as possible? It's all about accuracy. Okay, so the accuracy of the approximation depends on what we say the order of accuracy of our finite difference method. And this is the same for any other. Those of you who do ODEs, you'll be talking about first and second and fourth order sort of Adams methods and Runge-Kutta methods. That's the same thing. Okay, the order of your method, the higher the order of the method, the more accurate it will be. We can also reduce step lengths. Okay, so there's two ways in which we can increase the accuracy of our numerical solution. One is to use a better method, a higher order method, and the other is to use smaller step lengths. So remember the those H values, which we were doing last week. The smaller the H value, the more accurate your solution. But the smaller the H values, the more work we're having to do. So there is a trade-off between accuracy and work. Okay, so just mention a bit more about finite differences. I don't think I actually put this up last week, which is kind of remiss of me. Okay, this arrow here, this is your X domain. So it's just a straightforward real number line. Okay, and what we have is U is any function. So U can be any function. When we're solving PDEs, U is what we want to be the solution. Okay, what we think the solution is. So we're approximating that function U. Now, what we do with finite differences is we split up our domain into lots and lots of points. And those are points called nodes. So each of these dots on this X domain is what we call a finite difference node. Okay. Now, if I wanted to calculate the derivative at this point here, I need some values from the neighbouring points. Remember, a derivative is like, think of it as a slope. Okay, it's the rate of change. So, in very simple terms, a derivative is like a slope. Now, to be able to calculate a slope, I need at least 2. I need at least 2, but the more points I can include in my approximation, the more accurate it will be. Okay. Each of these points is a step length apart, so a length h apart. Most numerical methods all stem from this Taylor series. Now, this is just an infinite series approximation of U of x plus h. Okay, so we've got an infinite series, and basically, the more terms in our Taylor series we include, the better our approximation. But of course, the more calculations we're having to do. So what we do is we truncate the Taylor series. We ignore lots of the terms. So for example, this is my first order term. If I ignore all of these terms following it, I have a first order approximation of ux plus h. If I include the second order term, but ignore anything following that, I've got a second order approximation, and so on. So the more terms I include, the better my approximation. Okay. When we talk about approximation, we talk about error, we use this notation here, big O. So big O h to the n. What that isn't a value. Don't think of that as a numerical value. Think of that as a behavior. It's like a speed limit. Okay, what this says is as my step length decreases, as it tends to 0, this error, which is big O h to the n, or the behavior of the error, will also tend to 0, but at a rate at least as fast as h to the power n. So for example, if n was 2 and add a second order method, what that means is when I halve the step length, I'm cutting down on the error by a factor of a quarter. And what we do is we derive finite differences from the Taylor series, use them to approximate derivatives, and we have an algebraic system. So that's kind of recap of sort of what we went over last week. Okay, and we looked at these. Okay, these are, I'd expect you to sort of, at the end of this course, be able to memorize these, but these are the most sort of, well, not useful ones, but the most common ones. Okay, so here we have what we call a first order forward difference, and this is an approximation of the first order derivative. Okay, and all we do is we take the point to the right, so x plus h, minus the point at which we're trying to calculate, divide that by h, and that's an approximation of the derivative. And that's a first order approximation, because the power of h is 1. We can also go backwards. So this is forward, because we've got a step forward, or we can go a step backwards, and again, we have another approximation. We can have a better approximation by taking more values in our Taylor series, and we derive the second order central difference. So this is still an approximation of the first order derivative, ux, but this time we've got big OH squared. So this is second order. And this is step once to the right, minus step once to the left, all over to h. Remember, all these are approximating is just a derivative. And we've also got a second order symmetric difference. Now this is an approximation of a double derivative. Okay, and that's the second order symmetric difference. Now you can derive lots of those, and that's what lab sheet 2 is all about. But in practice, we don't bother deriving them because they've already been done. Okay. In a minute, I'm just going to talk about what we call a finite difference toolkit. But before that, I'm going to introduce a change in notation, because if you look at this, there's a lot of writing involved here. Mathematicians, by our nature, we're lazy. The less writing we can do, the better. So what's going on there? Okay, so I'm going to introduce the idea of a superscript and a subscript notation. Okay, remember, our u is in terms of variables t and x, or x and t, doesn't matter which way around they go. Okay, so our u is going to be a multivariable function. Sometimes you could have 5, 6, 7 variables. The ones we're going to look at have only got 2 variables. Well, later we'll be looking at 3. Okay, so what we do is the x variable is denoted by a subscript, the t variable is denoted by a superscript. Okay, so for brevity, i.e. to make things quick, we write this utx as uin. The I relates to the x direction, okay, how far we've gone along in the x direction. The n relates to the t direction. Okay. So, for example, I'm going to look at the bottom one first. If I want to use the central difference formula to approximate that derivative, Okay. As we saw on the previous slide, it's x plus h minus x minus h. Well, instead of x plus h, I'm going to write that as ui plus 1. So we've got one step to the right, minus ui minus 1. So the I minus 1 means we've taken one step to the left. And that's divided by 2 delta x. So we don't use h anymore because we've got 2 different variables. We use delta x and delta t, which is our step lengths. And this has an accuracy of big O delta x squared, so that's second order in x. Okay, the t is denoted by the superscript. Now this superscript isn't a power. Don't confuse this with a power, it's just like an index. And the derivative in the t direction, so this has nothing to do with the x direction, it's just the t direction, is one step advancing in t minus one step backwards in t, all over 2 times delta t. Okay, so the I on the bottom is your x index, the n on the top is your t index. This thing in the middle, just to remind you, when you take partial derivatives with respect to a variable, all other variables are assumed to be constants. So for example, if I was finding a partial derivative of u with respect to t, our x variable does not change. Okay, it's only with respect to that variable. Likewise, with x, we're taking the partial derivative with respect to x, our t variable does not change. Right, I mentioned before, but we don't usually, in practice, actually bother with deriving the finite differences because they've all been done for you. It's important we know how to derive them and where they come from, but in practice, we look them up. Okay, we have what we call a finite difference toolkit. These are lots of different finite differences, and we select the ones which we want to use. So you look at your derivative. So let's say we've got a first order derivative, and then you select what is the order of your approximation, how accurate do you want it. You may not always want it high accuracy, because high accuracy means more work. It means, generally speaking, your finite difference scheme or your numerical methods are more complicated. So there's all the finite difference approximations to the same derivative. Okay, each of these are approximations of the same derivative, just to different orders of accuracy. So that bottom one there, if you've made a start on lab sheet 2, that's what you've got to derive. You have a second order derivative, there are some. Okay. As you start to go down the derivatives, you need more and more points. So down here, if I had a fourth order derivative and to fourth order accuracy, you can see I need all of these points. Okay. Just be grateful I didn't ask you to derive that. So what we do, that's our toolkit. Just as a mechanic, when they're working on a car, they grab a spanner, whichever spanner they need to work on the car engine. We're mathematicians, we grab whatever tool we need from this toolkit to suit our needs. Right, so that's finite difference approximations. How do we solve a PDE? So that's what we're going to be looking at today. Okay. What we do is we derive a finite difference scheme. Okay. And we're going to be looking at this. This is a very simple PDE, one of the simplest, and it's called the advection equation. And all it does is it moves something from one place to another. Okay, so u is our function. Remember, that's what we're trying to find, that's what we're trying to approximate. So the derivative of u with respect to t plus v times the derivative of u with respect to x equals 0. That's what's known as the advection equation. Okay, so I just define a few things. X, have you seen this notation before? So that's membership. The square brackets means inclusive. So this means the range from A to B, including A and B. If it was rounded brackets, it would be exclusive, means not inclusive. Okay, so X is a spatial domain. T is time. U can be thought of as some concentration of a substance. Okay. The example we give is, imagine that you're stood by the side of a river Okay, and you've got a big bucket of some horrible, nasty pollutant, and you should throw the bucket into the river. What's going to happen to that pollutant? Well, the river's flowing downstream. That pollutant is going to get pushed downstream with the flow of the river. So imagine U is a concentration of that pollutant. V is a velocity. How fast does it move? Okay, so that'll be in meters per second. So if your river is flowing at 5 meters per second, and I throw something into the river, that's going to be carried down at 5 meters per second. If the initial conditions, so when t is 0, okay, if the initial conditions are some function of x, we have a solution. Very unusual for PDEs. We have an exact solution. That's simply f of x minus vt. Okay. So this is often used to actually test finite difference schemes to see if they work, because we can test them against this exact solution. Okay, so first thing we do is we split up our domain into lots of finite difference points. So there's our x domain. Okay, we've got two domains, we've got x and t. Okay, x is known as our spatial domain. So that's the one we split up. Okay, and what we do is we have one node at the very beginning. So that's our first value of x, is at A. And we label this one x0. Okay. You may ask why it's not x1. And the actual answer to that, you'll see in a minute. But one thing which is kind of complicated about this is we've always got one more node than this subscript here. Okay, so x equals A is our first node. N equals B is our last node. So that's our first point in our domain. This is our last point in the domain. And we label this one as x with a capital N in the subscript. And then we start to split up our domain. So let's say we're working with a step length of delta x. So our second node in from the left is going to be labeled x1, and that's going to have coordinates equals A plus delta x. The next one will be x2, and that'll be A plus 2 delta x. So you start to see the pattern. Whatever the subscript is, it's a multiple of our step length. So that's the first thing we do. We discretize our spatial domain. Okay, with discretizing the domain, either we know how many points we want and we calculate the step length, or we know the step length and we calculate how many points we need. So either one or the other. So we want this last point xn to be equal to b. So we want that equation there. All we do, very simple equation, solve it, and we get the number of points. So that's if we know what our spatial step is. We can calculate how many nodes we have. If, however, we know how many nodes we have, but we don't know the spatial step, we just transpose that. One thing you've always got to be aware of is because we're starting labeling at 0, the number of nodes we have is actually n plus 1. Okay, so remember, it's always the plus 1 as well. Okay, next thing we do, we derive the finite difference scheme. So that's our PDE. That's what we're trying to solve. So what I'm going to do is I'm going to replace this derivative here with a forward difference. Now I've chosen a finite difference from our finite difference toolkit and just replaced that there. Depending on the order of accuracy I want, depends upon which finite difference approximation I use. Okay, so I'm going to derive a very simple one here. I'm going to derive a first order scheme. So I've chosen a first order finite difference. Okay, and I've got to do the same for the spatial derivative. So this is my time derivative. So I take the forward difference in time. Okay, this is my spatial derivative. And what I've done here is I've selected a backwards difference in space, and I'll explain why in a minute. This wouldn't have worked with a forward difference in space. Just bear that in mind, and I'll come back to that in a minute. Okay, so what I've done here, by replacing the derivatives with differences, I no longer have an equation in terms of calculus terms. I now have an equation in terms of algebraic terms. And I could rearrange that equation to give me, well, what I want to rearrange it is so that this term, this is my new term, okay, step forward in time, so that this one is the subject. Okay, so subtract the second term from both sides, multiply both sides by delta t, and simple algebra, we get down to this. Okay. This is what I wanted, because what this means is the superscript n plus 1, that's my new solution. That's a solution at one time step at a time. All of these values with the superscript n are current solutions. So these are what I know. Anything with a superscript n are values we already know. The superscript n plus 1 is the unknown. So we stick the unknown on the left-hand side, the known values on the right, and that allows us to calculate what this is. Okay, one thing which, so this is what we end up with. So replace the finite difference approximations with, replace the derivatives with the finite difference approximations. So this approximates a solution at the next step using values at the current step. So n is your current step, n plus 1 is the next step. This is only an approximation of u. So big U was my solution. Remember, we're only ever approximating the solution. So it's common notation to use a lowercase character to denote the approximation. And since we use first order finite differences, our solution is going to be first order in time and first order in space. If I use a second order finite difference in space, it would be first order in time, but second order in space. So there'll be a 2 superscript after that. Okay, it's often useful to know or have a picture of how a finite difference scheme operates. Now, this is our scheme. Okay, what we do is we draw what we call a stencil. Now, going across on the horizontal axis, I have my space. Going up the vertical axis, I have my time. And we use the indexes I and I plus 1, etc. And n plus 1. So this is my current point, uin. Now this scheme uses uin and ui minus 1. So it uses those 2 points at that time level, n, to calculate the next point for I. Okay, so this point is calculated using that node and that node. So that's what we call a finite difference stencil. Now earlier I said this wouldn't work if I'd chosen a forward difference in space. Now the reason being is if we assume my velocity is positive, so the velocity is flowing from left to right. Okay. So here's, let's say I'm calculating whatever this is. As something comes in from the left-hand side, this node is going to realize it. Okay, so this node is going to realize we've got something coming in from the left, and this value will change. And therefore, because that value changes, so will that value. If I had a negative velocity, so I'm going from right to left, as I come in from this side, this feels a change before that one. Okay, so imagine this scheme is looking to the left. Imagine sort of it's facing that way. It can see something coming towards it from this direction, but it can't see something coming towards it from behind, and it wouldn't work. Okay, so when we're dealing with advection, when we're dealing with things moving, okay, we need to be able to tell or be able to see it coming, so to speak. Okay, almost there. Okay, so far we split up our domain. We derived our finite difference scheme. But we do have a problem at the boundary. Okay, so let's say this point was on the boundary. Nothing exists to the left of it. Okay, so if this is the boundary, this point needs this one to calculate it. But if that's on the boundary, nothing exists that side. So this is where we have boundary conditions. Okay, so for example, this point here, nothing exists to the left of it. It's right on the edge of our domain. So what does happen for this point? How do I calculate this point? The answer is I don't. I only apply my finite difference scheme to this point and onwards. So, okay, so this point knows about the value of this point, so I don't use my finite difference scheme to calculate that point. And likewise, at the other end, well, for the advection equation, that doesn't really matter, but for the convention, what we do, we can also have a boundary node at the upper boundary. So how do I calculate this point? The answer is I specify a boundary condition. So this node doesn't exist. So that node here, there's nothing there. Okay, so it doesn't exist. So what we normally do is we specify the value there. And we assume, for this example, I'm going to assume that value is going to be 0. Okay. Next week, we'll be looking at different types of boundary conditions. Okay, I think in your notes, yes, I'm going to have a look at just a couple of steps of an example. So this is my initial conditions. So this is the starting conditions. We always need that. We need initial conditions, we need boundary conditions for our PDE. I know it's initial conditions because t is equal to 0. And it's some function of x. And in this case, it's an exponential function. I'm going to use boundary conditions. So my boundary nodes, which is the first node and the last one, are always going to be equal to 0. And I'm going to use 11 nodes in my domain, and I'll have a velocity of 1 and a time step of 0.05. I need to specify all of that. First things first, discretize the domain. Okay, so I need to calculate the spatial step. Okay, that's b minus a over n, or n minus 1, sorry. I'm using 11 nodes, but remember the node numbering. Okay, n is 1 less than the number of nodes. Okay, so b minus a over n gives me a spatial step of 0.1. So therefore, my x coordinates start at 0, going up in steps of 0.1, that's finishing at 1. Okay, and that's the sort of same thing, but represented in a diagram. So you can see U0 is my first node. Okay, this is I've sort of done it as a white node because that's a boundary node, and UN, in this case n is 10, is also a boundary node. First thing I do, calculate the initial conditions. Okay, so that's the initial conditions, specifying what each node is. So what I do is I substitute in the value of x. Okay, so U0, well that's going to be 0, it's a boundary node, so for any value of t it's 0. U1, the x value was 0.1. So I replace x with 0.1 and calculate what that is. U2, well, x will be 0.2, and again, I calculate it. So the first thing I need to do is calculate the initial conditions. In this case, and this is not always the case, but in this case, delta t and delta x are constant. Okay. Later on in the term, we're looking at where delta t isn't constant, but for now it is. So v delta t over delta x, I should calculate at the beginning because it's never going to change. Just going to go back and, okay, so where did I get that from? Okay, that v delta t delta x, it's that number there. So that's going to be constant, so I can calculate that at the beginning. And then you just apply the finite difference scheme. That was our scheme. So the next value is equal to the current value minus 1/2 times the current value minus its left-hand neighbour. Okay, so U1, okay, is equal to the initial value of U1, which is 0.0001, minus 0.5 times its initial value minus its left-hand neighbour, which has a value of 0. You just plug it into a calculator or MATLAB or something, and it calculates. Do the same for U2. Again, its initial value minus 1/2 times its initial value minus its left-hand neighbour. Notice with this one, I've used that value there. I haven't used the one I've just calculated. That's very important. We can only use previous values. We can't use the n+1 values. Okay, right. So if you have a look at your on page 28 of the notes, what I want you to do is use that finite difference scheme to complete the sort of the empty squares in that table. I've accidentally already done one for you. Yeah. Okay, so do you not have your book? I haven't got any spares. Do you have one at home? Yeah, share some with somebody else's. Sorry, I don't know why the. Hey, there we go. Okay, so just to remind you, the scheme. Was it plus or minus? Normally minus, but I better check. Yeah, minus. Okay, so that was your scheme. So if I'm calculating this one here, okay, so that would be U3 1, because it's I is 3 and n is 1. That's going to be equal to U3 0 minus 0.5 U3 0 minus U2 0. Okay, so U3 0 is this number here, 0.3679 minus 0.5, that's multiplied 0.3679 again, minus its left-hand neighbour, 0.0183. And you just plug the values into a calculator. So what we got? 0.3679 minus 0.5 times 0.3679 minus 0.0183. And it's 0.1931. You don't have to write all this out for everyone. Okay, so that one will be 1 minus 0.5 times 1 minus 0.3679. So what I want you to do, just fill out the rest of that table. I'm going to round up to round to 4 decimal places. Okay, hopefully, don't wait for me to do them. Do it yourself rather than waiting for me just to write it down. So the whole point of this is we're using the numbers from the previous line to calculate the numbers for the next line. It's what we call a stepper algorithm. It steps forward in time using the previous or current values. And that's essentially what finite difference schemes are. Okay. Think about it, we've replaced the derivatives of finite difference approximations. Okay, and then we rearrange to make the UN plus 1 value the subject, and then you just plug it in, and it's fairly easy to compute. Okay. So in Blue Peter fashion, here's one I did earlier. Okay, just got to go down to the slide which we're on. Okay. And if you carry on doing that, you get those values. Okay, what I want you to do is just have a look at these values and take it line by line. Okay, well, it's quite difficult to do here, but this is our initial values. And if you look at what happens over time, what we see is we see our movement going in that sort of direction. Okay, so for example, at this end, here we've got quite a small figure. And as time carries on, that figure gets larger. Because what's happening is our movement, the advection of that pollutant is going down the domain. Okay, so that's this is the what's happening. So we've chosen quite a small number of points here. We've only chosen 10. So this should be like a nice smooth bell-shaped curve, but it isn't. Okay, so the red is the analytical solution. I mentioned the advection equation has an analytical solution. That blue line is our solution after 3 time steps. So you can see there's a fair bit of difference between the red and blue. The reason for that, there are two reasons. One, we use very few nodes, so our step length was quite large. If I'd have chosen 100 nodes, so our step length would have been 1/100th, okay, that would be a lot closer approximation. So the more nodes you take, the more accurate your approximation. The other reason why it's quite poor is this was a first order approximation. If I'd have used a second order, it would have been much more accurate. Okay, this is kind of like a flow diagram of the procedure. Just sort of, this sort of helps us when we want to write it up. Okay, and this is a generic flow diagram for a finite difference scheme. Start at the top. You start by initializing all our variables. Okay, so how many nodes we've got, what's our step length, what's our initial conditions, etc. We calculate our x coordinates, so that's a coordinate of our nodes and the initial conditions. Okay, this one, okay, set n equals to 0, n is going to be our sort of counter. Okay, how many iterations we've done. And n steps is going to be where we're going to stop. So if n is greater than n steps, if that's true, we've finished. We calculate the next values, update t, so t is then t plus delta t, update our u array, so we update our un plus 1 into un and add 1 to n. You can output it if you want, like plot it or something, and then keep going around that loop until you've finished, and then you've completed the loop. Okay, last week I had a bit of a moan because I kept you here for the 2 hour without a break. Would you like a 10-minute break now and come back later? Is that okay, or do you want me to carry on for an